Hello, my name is Leslie Rusch, and I'm a professor at Université Laval, Laval University in Quebec City, Quebec, Canada, where I work within the Center for Optics, Photonics, and Lasers, and in particular in the Optical Communications Laboratory. I'd like to thank the organizers of the conference for giving me the opportunity today to talk to you about research in silicon photonics for 5G communications. I'd like to begin by acknowledging my co-authors, Sun Guan, my postdoc, Mingliang Liu, my PhD student, and my collaborator, Professor Wei Shi. What I'm going to be talking today, I'd like to narrow it just down a little bit. It's not just 5G, but 5G in the context of smart edge computing. So as you know, we have many different kinds of devices accessing the networks today, and we use cloud paradigm to do a lot of the processing in the cloud. However, there are some applications for which the latency is too great when we go to distant cloud processing centers. And because of that, there's been introduced this concept of having an edge of the network, so a physical location close to the devices that are accessing the network. And in order to take advantage, to enable the low latency applications, we would move some computing processing to the edge of this network. So this is a general idea for smart edge computing, and I'm going to be talking about the intersection of this and 5G network enhancement. So this is an outline of my talk, and I organized it in terms of questions that I'll be answering. And the first question is, how do we evolve a radio access network, RAN, for installation at the smart edge? What can we gain when we do that? What can we gain with a RAN version of the smart edge? And how can we deploy how can we take advantage of already deployed passive optical networks, PON, in order to achieve this radio access network for 5G? Can silicon photonics enable a RAN for the smart edge? And I think you won't be surprised when I tell you the answer is yes. Yes, it certainly can. And where do we stand now? That's where I'll be telling you a little bit about the research that we've been doing in this area. Is it really that simple? That's where I give you some ideas on where perhaps you can make a contribution to continue examining this. So how do we evolve to a radio access network at the smart edge? So again, edge computing is to overcome the tight latency requirements and also the high computing power that may be needed by some applications. You can think of the smart edge as the Goldilocks solution. If I go far away to the cloud, I have lots of processing power, but the latency is high. If I do the processing in the mobile unit, the latency is low, but the processing power is also not available. So the smart edge, Goldilocks, short distance, latency low, but can put all the computing power we require there. So that's edge computing for applications. Now let's think about 5G communications. Well, 5G communications also has similar needs, and we call this the radio access network. And it also tries to deal with this concept of latency requirements of some applications and how to exploit cloud concepts. So the new problem that we have to solve in order to let 5G take advantage of this is, how do we deal with the remote antenna sites in 5G? How do we sign them up on this radio access network? How do they access edge computing? So let's start with just like what goes on when there is a 5G system with no radio access network. In this case, we have an antenna here. RU remote unit might be one way to refer to it, and it receives the RF signals, converts them, and creates a digital data signal which goes through what I'll call the backhaul network to reach the core network. Now, logically, we can think of all the processing that's done at the antenna site, and physically we can move some things away from the physical antenna at the top of the tower, put some things at the bottom of the tower. For instance, we can do the DSP and the distributed unit. We can have a central unit does more of the network level processing. But in any case, all of the baseband processing for the radio signals is being done now very close locally at the antenna site, if maybe at the base of the tower. To that, we can take this idea of edge computing and really make the edge be the antenna tower. And we could locate some computing power right there at the edge in this case being right at the antenna tower. And in this case, we have no latency issues. nothing I call bandwidth issues. Everything is taking place locally. Problem is, this is a great solution without a RAN, but it has very complex hardware at each one of the antenna sites, and the antenna sites might be not so interesting a place to put all this complexity. But even more important is there's no radio frequency coordination among different towers. One of the keys to 5G attaining the advances that they make in performance and in coverage and in speed is by exploiting coordination among towers, and that simply isn't possible without a radio access network. So we have this idea of smart edge. Okay, why don't I pull some of that processing away from the actual antenna site and put it in this smart edge, which really already exists because I have this multi-axis edge computing here already at this smart edge. So I'll pull some of the 5G work and I'll put it there. So the distributed unit still stays at the base of the antenna tower. So all baseband processing is still local. It's going on in this distributed unit. The computing power, as I said, is located at the smart edge, and so I take advantage of that physical location to be able to put some computing processing in the central unit in a pool to service what are multiple RF antenna units. So you think, oh, that's good. Now all my antennas are talking together. Well, not quite, because it's the distributed unit that handles the DSP processing. And therefore, the CU, the pool here, well, I guess I should back up a little bit. First of all, latency requirements are being met because we're at the smart edge and we're close. Because this distributed unit is doing all the DSP processing, as I mentioned, there are no bandwidth issues. There's no bandwidth expansion, and there's this mid-haul that I say is easy to do. The problem is that there's really no RF coordination. By the time these antennas get all of their signals that come to the central unit, I'm doing network level coordination, but I'm still not doing any RF level coordination because these distributed units are doing all the DSP. So this is the radio access network at the smart edge. So now what has changed? Now the distributed unit is actually located at the smart edge. And I've added a unit called the comp unit, and this is the unit that's responsible for the coordination of the RF signaling above the RU. The remote units. And something new I've introduced is something called the front haul, because now this part of the network has to carry RF signals, which hasn't been the case in any of the previous slides. So now I have to be able to carry RF signals in order to feed this comp unit, which is going to do the RF coordination. So RF coordination here at the comp. Latency requirements are met because we have this smart edge. And what's really great is there's no complex hardware here at the remote site, at the remote unit. This is just very, very simple processing. So what have we gained by moving to the smart edge? Well, we already have this idea of edge computing. We've got this multi-axis edge computing for apps. And now we've got the digital signal processing for the 5G also taking place in this edge computing environment. This allows us to achieve network densification. That means that we can have very dense picocells because each one of the units doesn't cost too much. And this will allow better coverage to increase 5G performance. And that comp unit I talked about, the real name is cooperative multipoint, and this allows the coordination at the RF level, which allows us to reduce the intracell and intercell interference, to enhance signal quality, and to just make everything work better for 5G. So what goes wrong when I move to this radio access network at the smart edge? And that's what I call bandwidth issues. So now that my optical fiber here has to carry radio signals, if I do a conversion from analog to digital, I will have a big expansion in the required bandwidth. And that has been a big challenge in moving to radio access networks. So what is our proposed solution? Well, we're going to overcome bandwidth limitations in the front haul by using analog radio over fiber, or ROF. This is to replace the common wisdom, which uses digital CPRI, or the Common Public Radio Interface. So instead of converting our RF signals to digital, having them require much more bandwidth, we keep analog radio over fiber, which keeps the remote units very simple, maybe even simpler than the CPRI solution, but at least no more complex. Another way to achieve this front haul of radio access networks in a cost-effective way is to exploit passive optical network infrastructure which already exists and to overlay our signals as a heterogeneous service in addition to the services already delivered on the passive optical network. So there is spectra available at the PON and the deployed fiber is already in place. So how is it that we exploit a PON for radio access network? Well, let's look at a PON. We're going to look at WDM PONs in particular because this is the future and we want to be ready for the solution which is future proof. So we have the central office which creates multiple wavelengths signals. They're all combined, they go over a single feeder fiber. It goes to the remote node or the smart edge, and at that point the signals are separated by wavelength and distributed to the different clients. And here we have the MEC server which does the edge computing for these broadband clients. So one thing we can do is we can actually add antennas as our clients. And in this case, these links, instead of being digital links, will be this radio over fiber link. But even more interesting, oh, and I should say here that I add the comp controller to the smart edge. This is where the digital signal processing is going to support these antennas. But even more interesting is to have these heterogeneous services so that on the same fiber here, I'm not only delivering this broadband service, but I'm also enabling extra antennas. So antennas that densify the 5G network by deploying very small picocells in addition to maybe what would be a larger client for larger antenna sites. So we'd like to use silicon photonics to really enable this smart edge happening for 5G. So what are the challenges? What do we have to deal with when we work with a passive optical network? Well, it's a single feeder. We only have one fiber for uplink and downlink. We want to use colorless operation. That means that the only light source is located at the central office. And this distributed carrier goes to each one of the users and it is remodulated to create an uplink. And of course, the uplink's a bit weaker. We also have, for this overlay I'm talking about, to think about the coexistence of these digital transmissions with this analog radio over fiber. And how are we going to do that? Well, first of all, silicon photonics is a great cost-effective solution. So we want to work with WDM networks. We want to be able to scale silicon or just an integrated solution that's going to do that better. And in particular, we'll be looking at micro-ring resonators as the silicon photonics solution because it is scalable to many channels, able to work for many WDM channels, future-proof. And due to the small footprint and small power consumption, this is an especially appropriate solution. So here are three different ways that silicon photonics can help us enable the smart edge radio access network. I divide the network into three locations. There's the central office, there's the smart edge of the network, and there's the customer premises or optical network unit, ONU, hardware. So at the central office, we have we can use micro-ring modulators in order to modulate data for each one of the broadband users in the PON. At the smart edge, well, at this point, this is where we add on our radio over fiber signals onto the already existing broadband signals. And then at the ONU, well, we have to separate all these disparate signals and receive them efficiently. So let's start at the central office. At the central office, we have a cascade of micro-ring modulators. We see them here in a Mach-Zehnder configuration so that they can provide complex modulation in an IQ modulation. And so we would simply have one of these IQ micro-ring modulators for each one of the wavelengths, which is going to be exploited. And in particular, why do we use IQ? It's in order to create a single sideband, which is very important for passive optical networks when we're trying to avoid fading due to chromatic dispersion during transmission. At the smart edge, what do? Well, again, microwave modulators are key. Again, we're going to cascade them, not necessarily IQ versions in this case. First, we're going to use, think of us as using a cascade of 3 microwave modulators for one WDM channel. The role of the first microring is to create subcarriers. So I create from a WDM main carrier 2 side subcarriers, and then the other 2 microwave modulators modulate onto these subcarriers and can be locked to a single wavelength here. And we could use either a baseband or a RF carrier modulation onto these subcarriers. And then all of these signals are passed on to the network, both the broadband, which is still there, and the analog radio over fiber, which we have added on using this cascade of microwave modulators. At the customer premises, what do? Well, first of all, we need another microwave modulator for the uplink and an IQ modulator. We also have to detect both digital and radio over fiber signals. So we're going to use the microring resonators for filtering and dropping signals, and we're going to use the microring modulator for the uplink portion. So for instance, we would have one microring resonator would drop a radio over fiber signal, then the next one perhaps, well, the first one would do, the broadband signal, the next one would do a analog radio over fiber signal, and the last one would drop another one. And finally, as it gets through this cascade of microwave resonators, when it gets to the microwave modulator, there will only be the residual carrier left, which is remodulated and sent back out. So we need multiple rings just so we can cover multiple signals, and all of this can be fully integrated in silicon. And a sort of useful outcome of the fact that the network itself does not want to deploy optical sources at the ONU. It wants to keep the inventory and complexity down and uses instead a distributed source. Well, that's just great for silicon photonics, for which creating light is difficult, but it's not necessary in this application. So I said that I would come to where do we stand now? So what's the research that we've been doing? So we've done some demonstrations for the Smart Edge. We did a microwave modulator layout. We fabricated the chip, and in our Clio 2020 paper, the reference is here. You'll be able to learn more in detail about these results. You can see here a photograph of the fabricated chip where we have multiple microwave modulators for the demonstration. So this was the experiment that we ran. We generated our digital signal as if it was coming from the central office, and then we have our microwave modulator cascaded chip here where we're adding on the radio over fiber signals. So we have a clock source that creates the subcarriers, and then we have a digital data log converter or a arbitrary waveform generator that generates our analog radio over fiber signals and puts them on the signal. From that, we go into just to have test equipment that recreates the ONU. We're just testing in this part the Smart Edge version. And so here we have a snapshot of the spectra that we created from our Smart Edge chip. If you look at this box in green, that sets out the area for the broadband services. And we have our main carrier here, and then we can see here the wideband signal, and we chose to do OFDM. We could have done Nyquist, QAM, we could have done PAM on a carrier, but we chose to do OFDM. And these are the signals to which we're going to add our radio over fiber. So over here is the second WDM channel, and you can see we have space in this case to create some new subcarriers. And on the subcarrier here we have a baseband radio over fiber signal, and here is a ROF signal on a 3 gigahertz carrier. So these are the results of our transmission of all of these various signals. So we have a 5G radio over fiber signal of 5G, which was the baseband version of that, and also a couple of OFDM signals. And we can see that we can maintain good performance over both bands despite having these overlay of 2 different kinds of services. And again, I refer you to our Clio paper for more details. In terms of the customer services, now we again have designed and fabricated a subsystem to deal with the requirements at the ONU. We have again a cascade. We have microring resonators, which are tunable, that allows us to tune both the central frequency and the bandwidth, that lets us pick out whether we're going to strip off a radio over fiber signal, as here, or whether we're going to go for the broadband signal like we see here. And finally, there is a microring modulator where we have carrier remodulation for generating the uplink. So we fabricated the chip, and we demonstrated the efficiency of this solution for doing detection of these very disparate signals within 1 WDM slot. So here I have the experiment that we ran for the ONU. Here is a sketch again of the components: a microring resonator for ROF detection, followed by one for OFDM detection, and then the microring modulator to remodulate the carrier for the uplink. So here is in black is the original spectra that comes into this subsystem. There's a big carrier. In this case, I think we did 5 different radio over fiber channels on one subcarrier. And then we have the broadband signal, again an OFDM signal in this case. Now we go through the first tunable microring resonators, and you can see sort of in orange, we tune the center frequency to be where the radio over fiber signals are, and we adjust the bandwidth so it's just wide enough to drop these 5G signals, peeling off just a little bit of the carrier power, just enough to have good, reliable detection, and to not cut off too much on our OFDM signal. Then we go through the next microring resonator. We're dropping this broadband signal, again peeling off just enough carrier to do good direct detection. And then finally, after the OFDM is dropped, we have this blue signal, which is the carrier with very low residual signals that we use for remodulation. And the carrier remains pretty strong because we didn't take off much power for our detection. So finally, after we have stripped off all of the downlink signals, we're left with something that is mostly the carrier. Here we can see just a little bit of the residual downlink signal, not much. And we use our microring modulator to remodulate this signal and create the radio over fiber signals in this case for the uplink. That was the demonstration we do. Of course, we could have also demonstrated the OFDM uplink. So the last part of the talk is really, is it that simple? What have I left out, and or what other opportunities are there to contribute to this area? And what are the complications? Well, clearly the stability of microring resonators has always been an issue, and we need demonstrations to show that the configuration we use, where we create subcarriers, which after all are slave to the master carrier, that the stability issues for these signals within one slot is very manageable. It will certainly add some complexity, but again, all this will be integrable. So nice demonstrations to show that this concept is indeed achievable. The next challenge is really in the polarization sensitivity of the silicon photonics. What we need is a polarization diverse design What we've done in all the demonstrations so far is to align all of our signals to one polarization, so it's